Hello everyone, my name is William Schupak. Today I'm going to discuss about a lattice-Boltzmann method used to simulate thermal convective flows using an orthogonal curvilinear coordinate system. This work is in collaboration with my colleagues Iman Yahia and Canon Premnath. In this work we have two primary objectives. The first is to improve efficiency of the lattice-Boltzmann method by using body-fitted grids in orthogonal curvilinear coordinate systems. The second is to improve numerical stability using a central moment-based collision model developed using the Fokker-Planck equation. During this talk, I will introduce you to the general governing equations for thermal convective flows in the OCC system, as well as the lattice-Boltzmann method, which we use to solve these equations. And then I'll discuss about how we improve stability using a Fokker-Planck based central moment collision model, and I'll follow up with a few benchmark test cases validating our model. To begin with, we define the relationship between a uniform square grid and the corresponding orthogonal curvilinear coordinate body-fitted grid using the metric factors shown here, as well as the curvature coefficients that represent the sensitivities of these metric factors in each direction. I'd like to point out these formulations are commonly found in the literature, and we've taken these from ASTFE and Veron. Then, using these relationships, the mass, momentum, and energy conservation equations can be defined in the general orthogonal curvilinear coordinate system, and what we want to do here is develop a lattice-Boltzmann method to solve these equations. The Boltzmann equation was originally developed to model distributions of fluid particles moving around, streaming, and colliding in velocity space. The Boltzmann collision integral modeled binary collisions, and by solving this equation, one could obtain the macroscopic fluid properties, mass and momentum, by taking moments of the distribution function in velocity space. On the other hand, by discretizing this equation and restricting particle motions to move along discrete lattice lengths, and also creating a model for the collision integral, we get the lattice-Boltzmann equation, which can be solved numerically through a process of simple streaming and colliding, and then the fluid properties can be recovered via finite sums instead of infinite integrals, dramatically simplifying the process. The collision integral is usually modeled as a relaxation process toward an equilibrium state, where the equilibrium state is generally defined using the continuous Maxwell distribution, which reflects the random nature in the collision process. On the other hand, relaxing moments of the distribution function allows us to apply different relaxation rates to different moments and improves accuracy and stability, but relaxing central moments allows us to apply a moving reference frame, enhancing Galilean invariance, and greatly improves accuracy and stability. The Fokker-Planck equation was originally used to model Brownian motion, which is particles whose motion comes from the effect of random molecular agitation. On the other hand, it's also equivalent to a Langevin equation, which has stochastic and deterministic terms. The Fokker-Planck equation has also been extended to model hydrodynamics. It can be used in the lattice-Boltzmann method framework, and what we propose is a central moment-based collision model using this equation, and we also allow the diffusion coefficient to vary in different directions using a tensor-based diffusion coefficient, and later we relate this diffusion coefficient to the variance of the distribution function itself, which is effectively a second-order central moment. To construct the central moment collision operator, first I'll define what a continuous central moment is using some notation. First is the inner product of two objects, A and B, as the integral of A times B over all velocity space. The second is the central moment weighting factor, which are components of the particle velocity shifted by the bulk fluid velocity raised to powers m and n. And then the continuous central moments of order m plus n are defined as the inner product of the distribution function with the central moment weighting factor. Then we define the rate of change of continuous central moments due to collision by taking the inner product of the Fokker-Planck equation with the central moment weights, and after integrating exactly term by term, we get a relationship that represents the relaxation of central moments toward an equilibrium state, where the equilibrium state, as this equation shown at the bottom, is a function of the lower order central moments themselves. And then we take a step further and say the diffusion coefficient is related to the variance, or the spread, of the distribution function, which are also second order central moments. Using a Chapman-Enskog analysis in moment space, we can demonstrate that our lattice-Boltzmann method will recover any given governing equation if, first, the moment equilibria are chosen very carefully and correctly. In fact, some of them show up directly in the governing equations themselves. Other additional terms in the equations involving spatial gradients that show up as parts of the viscous stress tensor in the OCC system are accounted for by using equilibria moment corrections, and all of the rest of the terms in the governing equations are accounted for in the lattice-Boltzmann model by including geometric source terms. To construct our lattice-Boltzmann method, we discretize along a D2Q9 lattice so that we have 9 velocity directions. Using those directions, we construct a non-orthogonal moment basis, which is used to transform into moment space. Then we define the discrete raw moments and the discrete central moments of order m plus n, allowing us to map between distribution function, raw moments, and central moments. Then we can list the central moment equilibria that we have chosen to recover the hydrodynamic equations in the OCC system, where the highest order central moment equilibria at the bottom is chosen based on the Fokker-Planck collision model, which acts only to improve stability of the model and does not affect the hydrodynamics at all. In addition to that, we also define the moment equilibria corrections and the central moment source terms that are used here to recover the governing equations in the OCC system, where these various parameters, coefficients, and force terms are functions of the OCC parameters, the metric factors, the curvature coefficients, as well as the conserved flow variables, the density and velocity components. Finally, using these discrete central moments, we can perform collision by first mapping distributions into raw moment space, then into central moment space, where we relax our central moments toward the defined equilibria, accounting for additional source terms and equilibria corrections. And then we map back into velocity space where streaming is performed, and finally recovering hydrodynamic variables. So the simplicity of the stream collide process is maintained in this model. Moreover, to solve the energy equation and obtain a temperature field, we solve a second distribution function, LB equation. Here I'm showing the corresponding central moment equilibria for that equation, and again we're using the Fokker-Planck based equilibria condition for the highest order central moment equilibria here. And then to solve for fluid and temperature fields at the same time, we solve both of the lattice-Boltzmann equations simultaneously, obtaining fluid properties and temperature field. Sometimes these are coupled. And again, the simplicity of the stream collide process is maintained in both of these models. Our first benchmark test case involves a polar lid-driven cavity in which a polar cavity with a moving wall that has a tangential velocity of r omega is simulated. We map this grid into a computational domain where we solve our lattice-Boltzmann model, obtaining the solution, and then we map those results back into the physical domain. Now, because we're using cylindrical coordinates for this problem, there's an exact conformal mapping by using these equations here, we're able to map back and forth using an analytical expression, but in more general cases, an orthogonal grid generator could be used to obtain these parameters. We run this simulation for two different Reynolds numbers, 60 and 350, and we compare the streamlines with those found experimentally by Fook and Tillmark, and we find that our flow field looks very similar to theirs. On the other hand, to get a more quantitative comparison, we look at the radial and angular velocity profiles along different angles in the radial direction, and what we do is we compare to the experimental results and numerical results by the same comparison case, and we find that our results match very nicely with theirs. We do this again for a Reynolds number of 350, and we find very similar results. In addition to that, we also run cases at Reynolds number of 1000 and 2000, and we compare with the numerical results provided by Shen and Xu, and we find that our results match very nicely with theirs. Then, to understand the stability features of our Fokker-Planck model, we do a stability comparison using lid-driven cavity case, and what we do is we run three different collision models, a raw moment-based collision model and a central moment-based collision model, both using Maxwell's distribution, and we compare our Fokker-Planck central moment collision model with the results from these two models. And what we do here for different grid sizes, we ramp up the Reynolds number up until the point where the simulation becomes unstable, and we note down the maximum Reynolds number that each model is able to simulate before it becomes unstable. And then we compare across the different collision models. What we find here is that the Fokker-Planck based collision model is able to reach much higher Reynolds numbers than the other two models. Our final benchmark is the natural convection in an annulus between two cylinders. The inner cylinder has a constant and uniform hot temperature, while the outer cylinder has a constant and uniform cold temperature. The flow field here is modulated by the Rayleigh number, which is chosen as 5 × 10⁴ power. This number is consistent with the experimental results provided by Keelan and Goldstein. And in this model, we couple our fluid flow solver to the temperature field solver using the Boussinesq approximation. Again, we use the same kind of cylindrical conformal mapping to map from the physical domain to a computational domain, which is where we solve our Lattice-Boltzmann method, and then after obtaining the results, we map back into the physical domain. To compare our results, we first look at the temperature field in the entire domain, and we compare with the experimental results of Keelan and Goldstein. We notice that the temperature profiles look very much similar to what they found experimentally. However, to get a more quantitative comparison, we look at the temperature profile along radial lines at different angles, 0 through 180 from top to bottom, and we find that our temperature profiles match very nicely with those produced by Keelan and Goldstein experimentally. In addition to that, we look at the equivalent thermal conductivity on the inner and outer cylinders produced by the same reference, and we find relatively good agreement. In conclusion, we've developed a central moment-based Lattice-Boltzmann model formulation to solve thermal convective flows in an OCC system, which improves efficiency because we're using body-fitted grids. In addition to that, we've applied a Fokker-Planck central moment collision operator, improving stability. We've demonstrated these properties using standard benchmark test cases, which indicate stability and accuracy of our model. In the future, we plan to investigate further using traditional CFD orthogonal grid generators to simulate more general complex thermal flows. Thank you for listening to my talk. If you have any questions, please ask them now or feel free to email me. Thank you.